A perfect stone block holds more than just weight. It contains a forgotten code. This is the mathematical language of ancient builders, a sophisticated system of geometry that allowed them to construct wonders which have stood for centuries. By the end of this exploration, you will be able to look at any ancient structure and see the hidden calculations etched into its very form. We will uncover how master masons used secret ratios to make walls defy earthquakes and designed windows to capture celestial light. What forgotten wisdom do you think is locked within the world's oldest stones? That single block of stone, with its crisp angles and smooth faces, is far more than a building component. It is a physical expression of an entire philosophy, one we call stone geometry. This is the practical and deeply symbolic application of mathematical principles to the art of building. Master masons used proportion, symmetry, and modularity as their core vocabulary. They took raw, chaotic material from the quarry and transformed it into a coherent architectural whole, a silent language written in rock and mortar. The renowned art historian Otto von Simpson beautifully described medieval architecture as frozen music. He saw the geometric ratios in a cathedral's design creating a visual harmony as precise and moving as a musical chord. This pursuit went far beyond mere structural strength. It was a way to convey cosmic beliefs, societal order, and a search for divine perfection through the very arrangement of stone. Consider the simple yet profound act of determining the angle for a vault rib. This required a practical understanding of triangulation, a straightforward engineering calculation. Yet for the builder, it was simultaneously a spiritual exercise, an act of aligning human creation with the perceived order of the heavens. Every stone was a single word, carefully chosen and placed to form a larger, meaningful sentence. So what were the specific mathematical tools these master builders used to write this enduring language in stone? The tools were simple: a compass to inscribe perfect circles and a straight edge to draw unwavering lines. Yet in the hands of a master mason, they became keys to unlock cosmic order. With these instruments, the endless division and multiplication of simple ratios could generate the breathtaking complexity of a Gothic cathedral's floor plan. Proportion was the foundational grammar of their stone language. They worked with ratios like the golden section, a number roughly equal to 1.618 that appears throughout nature, and with simpler, whole number relationships like 1 to 1, 1 to 2, and 2 to 3. These were not arbitrary choices. They were believed to reflect the very harmonic structure of the universe, a divine mathematics that could be mirrored in human creation. The Roman architect Vitruvius famously argued that a building must imitate the proportions of a well-formed human body, a concept that medieval builders eagerly adopted and spiritualized. They saw their cathedrals as microcosms, small-scale models of God's perfectly ordered creation. To achieve this, they employed elegant geometric systems known as ad quadratum, based on the square, and ad triangulum, based on the triangle. From one single initial measurement, often the width of the nave, they could generate every major dimension of the entire structure. The height of the walls, the span of the arches, the placement of the windows, all were mathematically linked back to that first decision. This is why such spaces feel so intuitively right and balanced to us, even when we are unaware of the silent numbers governing the stones around us. We sense the deep, underlying coherence. But this pursuit of perfect proportion leads to a pressing, practical question. How did these abstract ratios, so elegant on parchment, contend with the immense, crushing weight of real stone? From that elegant geometry on parchment came the thunderous reality of the quarry. Master masons faced a monumental task: transforming abstract ratios into thousands of physical stones that would fit together flawlessly. Their solution was a system of brilliant efficiency known as modular design. Imagine a chaotic quarry slowly yielding hundreds of nearly identical stones, not through random chance, but because the masons worked from a set of standardized templates or modules that dictated the size and shape of each block. This was the practical engine of stone geometry. A few standard block dimensions could be combined in countless ways to create vast and complex structures with incredible speed and precision. This approach minimized stone waste, dramatically sped up construction timelines, and allowed for the training of large, dispersed workforces. A stonecutter only needed to master the cutting of a limited set of forms to contribute to a project he might never see completed. The Cistercian monks, for instance, were absolute masters of this system. They used a strict modular blueprint to rapidly build their austere yet geometrically perfect monasteries across Europe. Each new monastic site faithfully replicated the proportions and modules of the mother house, creating a network of buildings that all spoke the same silent architectural language. This system also possessed a beautiful democratic quality. While the master mason alone held the overall secret of the design in his mind, every single stonecutter, by perfectly executing his standardized piece, contributed a vital part to the grand puzzle. The overwhelming success of this modular approach, however, hinged on an even more fundamental skill: the crucial ability to transfer a grand design from a small sheet of parchment to the rocky, uneven ground of the building site. That grand design, conceived in the mind of the master mason, had to find its way to the earth. The critical translation happened not on small sheets of parchment, but across vast, flat plaster floors known as tracing floors. Here, in a process called setting out, the entire building was drawn full scale, a ghostly blueprint etched in chalk and string. This was the moment when abstract numbers and ratios became a tangible guide for human hands. Every curve of an arch, every angle of a vault, every delicate tracery of a window was laid out with painstaking precision, solving complex geometric problems in 2 dimensions before a single stone was ever lifted into place. These immense drawings were the true heart of the construction project, a shared reference that allowed dozens of artisans to work in perfect harmony. From these lines, carpenters would cut thin wooden templates or patterns for the stonecutters. A stonecutter in a quarry miles away, holding one of these wooden shapes, knew exactly what to carve. He did not need to understand the grand theological meaning of the cathedral, only that his block must match the template perfectly. This system guaranteed that stones shaped by different people in different locations would lock together without a single millimeter of error when they finally met high on the cathedral wall. The famous labyrinth set into the floor of Chartres Cathedral is often walked as a spiritual meditation, yet some researchers propose it also served a profoundly practical purpose: a permanent geometric reference point used by the master builders to set out and check the proportions of the immense structure rising above it. This meticulous art of templating reveals a stunning truth. The builders' genius was not just in their physical strength, but in their foresight. Their most profound work was often done on their knees, drawing in plaster, long before the first cheer went up for a newly placed stone. This deep integration of planning and execution rested upon a very specific and surprisingly disputed understanding of the world's fundamental shape. Within the quiet of a medieval mason's workshop, the air was thick with stone dust and concentration. The true masters of this craft wielded a toolkit of elegant simplicity: a compass for the perfect curve, a square for the unwavering right angle, and a length of knotted string for translating grand designs across vast distances. These were not mere instruments, they were philosophical extensions of the builder's hand, physical representations of the cosmic order they sought to emulate in stone. The compass, tracing its endless, unbroken circle, symbolized the divine and the celestial. The square, with its firm and fixed corners, represented the solid, material world of humankind. Their work was a constant act of bringing these two realms into harmony. We can still peer into the mind of such a master through the pages of the 13th century sketchbook of Villard de Honnecourt. Its pages are a breathtaking testament to this geometric thinking, filled with intricate constructions that show how the entire world, from the delicate features of a human face to the sprawling plan of a cathedral, could be generated from circles, squares, and triangles. This was the universal language, and these three tools were its alphabet. The humble string, often overlooked, was perhaps the most versatile tool of all. By tying knots at precise intervals, a mason could create a living ruler. Stretched across a building site, 3 strings of lengths measuring 3, 4, and 5 units could form a perfect right-angled triangle, a direct application of the Pythagorean theorem used to ensure that foundation walls were perfectly square with the world. This exact same technique is used by carpenters and builders to this very day, a direct thread connecting our modern world to the silent knowledge of the medieval mason. The beautiful constraint of this limited toolkit did not stifle creativity, it unleashed it. Forced to work within the pure language of geometry, these builders discovered the profound and eternal relationships that structure our reality. They were not just drawing lines, they were decoding the universe itself, and they often chose to encode their deepest understandings not in words, but in the silent, stone symbols they left behind. That 5-petaled rose carved into the cathedral stone is far more than a beautiful flower. It is a perfect pentagram, a geometric form believed to hold immense power and meaning, silently declaring its presence to those who could understand its language. This is the world of symbolic geometry, where every circle, square, and triangle was a vessel for profound ideas, transforming the entire building into a stone library of spiritual wisdom. The circle, with no beginning and no end, was the universal symbol for heaven, eternity, and the divine. The square, grounded and stable with its 4 equal sides, represented the earth, the 4 cardinal directions, and the 4 classical elements. The triangle, a shape of immense structural strength, was often used to represent the Holy Trinity. You can see this philosophy in the very footprint of a great cathedral. The congregation worshipped in the rectangular nave, the square space representing the material world. Their gaze, however, was drawn forward and upward toward the soaring vaults and the great circular rose window, a symbolic portal to the heavenly realm. This was not just decoration, it was a carefully choreographed journey from the earthly to the divine, built in stone. For the master mason, a complex geometric exercise was never just about mathematics. The challenge of perfectly inscribing a circle within a square, a problem known as squaring the circle, was also a deep meditation on how the spiritual permeates the physical world. His compass and straightedge were tools for both engineering and enlightenment. This symbolic coding invites a fascinating question. If the very shapes of the building held such cosmic meaning, did the builders also look to the heavens above to guide their hands below? The long, dark passageway of Micho tomb becomes a brilliant corridor of light for just a few moments each winter solstice. This architectural marvel, built millennia before the great cathedrals, proves that aligning stone with the stars is one of humanity's oldest intellectual pursuits. These builders were not merely stacking rocks, they were creating a permanent instrument to track the cosmos itself, a stone calendar that marked the year's most significant turning point with a shaft of golden light. This profound principle, the sacred dialogue between architecture and astronomy, became a cornerstone of the medieval builders' geometric language. They looked upon the heavens and saw a perfect divine clockwork, a celestial mechanism of such intricate order that it could only be the work of a master geometer. By mirroring that cosmic order on the ground, they believed their buildings could become bridges connecting the earthly realm with the heavenly one. You can see this intention in the very orientation of a Gothic cathedral. The high altar was almost always placed at the eastern end, carefully aligned so that the rising sun on the patron saint's feast day would flood the sacred space with light. This was not a vague hope, it was a precise calculation. It required the master mason to possess not just surveying skill, but a deep, practical understanding of the solar calendar, knowing exactly where the sun would break the horizon on one specific day of the year. This celestial choreography transformed the entire building from a static object into a living participant in a cosmic dance. The geometry of the stones was in constant conversation with the geometry of the skies. This grand vision of integrating human creation into the universe's own design finds its ultimate and most complex expression in the master mason's final and most challenging test, the intricate stone skeleton of the vaulted ceiling. That delicate stone tracery holding the great windows of Sainte-Chapelle is a geometric marvel in its own right. It forms a skeletal web, a lacework of stone that allows the walls to become immense canvases of colored light. This was the Gothic builder's ultimate ambition, to dematerialize the wall itself, transforming heavy stone into a vessel for divine illumination. Their mathematical language was now being used to master a new element, emptiness. The precise geometry of the window openings was calculated to do more than just let in sun. It was designed to control and magnify it, to transform raw daylight into a spiritual medium that told sacred stories. The most breathtaking examples of this are the great rose windows, which are essentially massive, stone-framed geometric diagrams. Their complex, radiating patterns often symbolize the wheel of fortune or the ordered perfection of the celestial spheres. Each piece of colored glass is set within a framework generated from circles and arcs, making the entire window a cosmic map and a theological lesson written in light and stone. But such brilliance came with a profound structural challenge. How do you hold up a heavy stone roof when you have replaced the supporting walls with vast, fragile windows? The answer was another geometric innovation, the flying buttress. These elegant stone arms leap from external piers to the high walls, channeling the crushing weight of the vaults along carefully calculated arcs and down into the ground. This external skeleton of stone allowed the internal skeleton of the building to become a fragile seeming cage of light. The true magic of this system is its harmony. The geometric principles governing the curve of a buttress are the same ones that dictate the branching pattern of the window tracery and the proportions of the vaults inside. Every element speaks the same mathematical language, creating a unified whole where stone and light, structure and symbol are inseparably fused. This pursuit of luminous verticality leads us to the final and most awe-inspiring application of their art, the intricate stone webs that seem to float high above our heads. High above, the stone ribs of a Gothic vault converge like the branches of a celestial tree. This intricate stone web is the ultimate expression of the medieval builders' geometric language, a final, breathtaking test of their skill where mathematics and masonry became one. The creation of a vault began with the centering, a massive temporary wooden framework that supported the stones until the final keystone was locked into place. The precise curve of each rib was not guessed. It was plotted on the tracing floor using compass sweeps and triangulation, ensuring that every block, often cut miles away, would meet its partner in perfect alignment hundreds of feet in the air. The weight of the vault was immense, but it was a controlled force, channeled deliberately down the ribs to specific points on the piers below. This is where the geometric foresight of the master mason proved its worth. He knew that the complex, seemingly fragile net of stone overhead was not a decorative afterthought. It was the primary structural engine, a stone skeleton that distributed forces with the elegant efficiency of a spider's web. The most sophisticated of these, the fan vault, appears as a stone waterfall frozen in mid-cascade. Its construction was a geometric tour de force, where every concave panel was a segment of a perfect cone, all generated from the same central point and radius. To stand beneath such a vault is to witness the silent power of mathematics made manifest, a ceiling that seems to defy its own weight through pure, calculated form. How did these builders achieve such a delicate balance between crushing mass and ethereal lightness? The answer lies not just in the vaults themselves, but in the revolutionary invention that made them possible, the flying buttress, an external skeleton of stone that allowed the internal stone skeleton to reach for the heavens. A hanging chain holds the secret to supporting a mountain of stone. The gentle, natural curve it forms, known to geometry as a catenary, becomes a principle of immense strength when flipped upside down. This is the perfect arch, a shape that does not simply hold weight, but masterfully guides it, transforming a crushing downward force into an outward thrust that is channeled safely down into the earth through the solid stonework of the piers. This single geometric insight is the silent heart of architectural stability, the reason a stone bridge can carry traffic for 1,000 years. The medieval builders did not invent this principle, but they refined it into an art form, using it to create the breathtaking rib vaults that crown their cathedrals. Look up into that soaring ceiling, and you will see a geometric grid of stone ribs, each one a carefully calculated arch. This grid acts like a stone skeleton, catching the weight of the roof and funneling it with pinpoint accuracy to specific columns below. But this created a new and dangerous problem. The immense outward thrust from these high vaults threatened to push the very walls apart. The solution was a stroke of genius, the flying buttress. These elegant stone arms leap from external piers to catch the thrust of the vaults, creating a dynamic balance of forces, a visible push meeting a visible counterpush that holds the entire structure in a state of perfect stone-woven tension. This external skeleton of buttresses is what allowed the internal walls to become fragile curtains of stained glass, transforming heavy, fortress-like Romanesque architecture into the luminous, skeletal frames of the Gothic style. This geometric understanding of compressive force was not limited to the north. In Florence, the challenge was not a vault but a vast dome. Filippo Brunelleschi, after deeply studying the ruins of ancient Rome, devised a brilliant solution, a double-shelled dome. His design used a complex geometric arrangement, with the inner and outer shells connected by a hidden web of stone ribs, creating a structure that was both incredibly light and monumentally strong, supporting itself as it curved inward to close the great space. Each of these triumphs, from the pointed arch to the flying buttress to the double dome, represents a different dialect in the universal language of structural geometry. They were not working from written theories or engineering textbooks as we know them. So how was this profound, life-or-death knowledge of forces and forms so perfectly passed from one generation of builders to the next, leaving no room for error? A senior mason's most valuable possession was not his chisel, but a secret held securely in his mind. Within the protective walls of the Guild Lodge, the master's geometric knowledge was passed from one generation to the next through a living chain of demonstration and practice, a direct transmission that bypassed the written word entirely. This was not a school as we know it. It was a ritualized apprenticeship, a slow and careful initiation into the mysteries of the craft. The guild functioned as a complete world unto itself, a powerful combination of a trade union protecting its members' welfare, a technical university for advanced geometry, and a fraternal order bound by solemn oaths that connected masons from England to Bohemia. Their methods were secret not because they dealt in magic, though some results must have seemed magical, but because this knowledge was the very source of their livelihood. The geometric formula for setting out a perfect spiral staircase or a self-supporting vault was intellectual property of the highest order, the key that unlocked prestigious commissions and ensured a steady income. This reliance on oral tradition meant the most sophisticated techniques rarely made it to parchment. This is why surviving manuscripts like the Regius poem, with its mix of moral instruction and craft rules, or the rough pages of Villard de Honnecourt's sketchbook are such extraordinary treasures. They are accidental windows into a world that deliberately kept its most profound understandings private. This system of guarded, practical education created something astonishing, a remarkable consistency in architectural technique across the European continent for centuries. A mason from Normandy could travel to a work site in Cologne and understand the geometric principles being used, the same language of squares, circles, and triangles governing the stonework. This shared knowledge wove a pan-European architectural tapestry, a silent conversation held across borders and languages, but the foundational ideas protected by these medieval guilds were not entirely new. They were echoes of a much older understanding, a primordial geometric wisdom that the guilds had refined and preserved. The stones of the Parthenon do not whisper of a forgotten past but speak a continuous geometric truth. Medieval master masons were not the first to hear this call. They were the latest in a long lineage of builders who understood that number and form were the language of creation itself. This tradition began with the ancient Greeks, who saw mathematics not as a dry science but as a direct path to comprehending cosmic beauty and divine order. For them, the ideal building was not just strong, it was a philosophical statement carved in marble. Their concept of symmetria, the perfect, harmonious relationship of every part to the whole, was the direct intellectual ancestor of the proportional systems that would later define the Gothic cathedral. It was a belief that true beauty could be expressed through simple, elegant ratios, a principle embodied in the flawless proportions of a Doric column or the subtle curves of a temple step. The Romans, in turn, became the great engineers and systematizers of this inherited wisdom. While they shared the Greek appreciation for proportion, their genius lay in practical application and scale. They perfected the arch and the dome, and their revolutionary use of concrete allowed them to inspace the world in a way never before imagined. Most importantly, they codified this knowledge. The Roman architect Vitruvius, in his foundational work De Architectura, laid out the principles of good building, arguing forcefully for durability, utility, and beauty. He explicitly connected architecture to the proportions of the human body, a concept that would echo powerfully 1,000 years later in the minds of medieval builders. The Roman army itself operated on a principle of modularity, laying out identical military camps and planned cities from Britain to Syria using standardized units of measure. This practice of modular planning is a clear and direct precursor to the Cistercian monks' use of identical templates to build their monasteries across Europe. It seems almost certain that handwritten copies of Vitruvius's work survived the collapse of the Roman Empire, carefully preserved within the scriptoria of medieval monasteries. There, learned clerics, working hand in hand with the master masons of the great cathedral projects, would have studied these ancient texts, adapting classical ideas about proportion and order to a new Christian context. This reveals a profound continuity. The so-called secret language of the medieval Masons was not invented in the 12th century. It was a powerful dialect of a much older, universal tongue, one whose first syllables were spoken by the pyramid builders of Egypt and the ziggurat architects of Mesopotamia. Yet the cathedral is not the only place where this geometric language was spoken. Across the ocean and long before the Gothic spires rose, the Inca of the Andes were composing their own masterpieces in granite. At sites like Machu Picchu and Sacsayhuaman, they built without mortar, shaping colossal blocks into complex polygonal puzzles. Each stone, with its unique, multifaceted edges, locks perfectly with its neighbors in a geometric embrace so precise that a knife blade cannot be inserted between them. This was not merely a stylistic choice, it was brilliant seismic engineering. During an earthquake, these intricately jointed walls dance, the stones shifting and settling without collapsing, a living testament to a profound understanding of stability through geometric interlock. Modern structural engineers study these walls not as ancient relics, but as sophisticated solutions to problems we still face today. How did cultures separated by vast oceans and millennia arrive at such similar principles of construction? The answer seems to lie not in shared blueprints, but in a shared confrontation with the same physical laws of weight and force. A similar echo of this ancient understanding resonates deep beneath the Mediterranean island of Malta. Here, at the hypogeum of Hal Saflieni, a subterranean sanctuary was carved from solid limestone around 5,000 years ago. Its chambers are not random caves, but carefully proportioned spaces that demonstrate an early and advanced grasp of acoustic geometry. Specific rooms, like the famous oracle chamber, are shaped so that sound resonates at a particular frequency, amplifying the human voice into a deep, pervasive echo that seems to emanate from the stone itself. This was likely intentional, a way to use the geometry of space to create an immersive, otherworldly experience for rituals and ceremonies. The builders were manipulating emptiness, using proportion and form to control an intangible force, much as the Gothic masters would later use stone tracery to harness light. These global parallels from the Andes to Malta challenge any narrow view of architectural history. They suggest that the drive to encode mathematical order in stone is a universal human impulse, a fundamental way we have always sought to create meaning, ensure stability, and connect with forces greater than ourselves. The medieval master mason, then, was not an isolated genius. He was a participant in a timeless, worldwide conversation, one where the vocabulary was composed of stress lines and harmonic ratios, and the sentences were written in enduring stone. A castle's soaring keep was a geometric argument against annihilation. Its transformation from a vulnerable square to a formidable cylinder was not a matter of style but a calculated response to the brutal physics of the siege. The weak point of any square tower was its corner, a fragile seam where attacking forces could concentrate their efforts, digging tunnels to collapse the foundation or pounding it relentlessly with heavy stones. A circular or polygonal tower, however, presented a continuous, deflecting surface. A projectile striking its curved wall was far more likely to glance off harmlessly, its energy dissipated by the geometry of the stone. This simple yet profound shift in form, from a shape with corners to one without, turned a static target into a dynamic shield. This defensive geometry extended to the smallest details, most critically the narrow vertical openings known as arrow slits. These were not simple holes in the wall. They were carefully engineered instruments of sight and fire. Their design followed a precise angular calculation, flaring widely on the inside to give an archer a broad field of view and a wide arc for shooting, while tapering to a slender slit on the outside. This principle, the field of fire, meant an attacker outside saw only a thin, difficult target, while the defender inside commanded a sweeping panorama of the approaching threat. It was a perfect marriage of protection and aggression, all dictated by the careful application of angles. The ultimate expression of this martial mathematics was the concentric castle. Places like Beaumaris in Wales were not just fortresses, they were geometric death traps. Their design employed multiple, perfectly circular or polygonal rings of walls and towers, one set inside the other. An invading force that breached the outer wall did not find safety. They found themselves trapped in a killing zone, a narrow corridor between the walls completely exposed to a crossfire from the higher, inner defenses. There was no place to hide, no angle that was not covered by an archer's line of sight. Every curve of the wall was calculated to maximize fields of fire and eliminate defensive blind spots. Here, the silent language of stone geometry speaks in a different, more urgent dialect. The same principles of circle and square that created spaces for spiritual contemplation in cathedrals were now deployed to ensure survival against overwhelming force. This reveals the incredible versatility of the master builder's knowledge. His compass and straightedge were tools for both enlightenment and endurance, capable of drawing a rose window to channel divine light or a bastion to deflect a barrage of stone. The intelligence required to build for the soul was the very same intelligence needed to build for siege. The language of stone geometry echoes across millennia, long before the first cathedral spire pierced the sky. Our Neolithic ancestors were the original masters of this craft, arranging colossal stones into circles and tombs with a sophistication that still challenges modern understanding. Their work proves that the human drive to impose mathematical order upon the landscape is a primordial instinct. Consider the sprawling alignments at Carnac in France, where thousands of standing stones march across the countryside in precise rows. The positioning of these megaliths reveals a clear, practical knowledge of Pythagorean triangles, creating perfect right angles over vast distances using nothing more than ropes and stakes. This was large-scale geometry executed with what we would consider primitive tools, yet the precision achieved is a testament to a deep and shared comprehension of form and measurement. The effort required to transport and erect these stones speaks of a society unified by a powerful common purpose, one that found its ultimate expression in the silent, enduring language of monumental stone. The Great Passage Tomb of Newgrange in Ireland offers perhaps the most stunning example. Its entrance is crowned by a unique roof box, a narrow opening engineered with exacting care. For just a few minutes at dawn on the winter solstice, a shaft of sunlight penetrates this aperture, traveling down the long passage to illuminate the inner chamber. This was not a happy accident. It required generations of builders to possess and then translate precise astronomical knowledge into a stable, durable stone structure, a project that spanned lifetimes. These prehistoric puzzles serve as a humbling reminder. The medieval master masons were not the first to speak this language. They were simply the latest in a continuous lineage of builders, inheriting a foundation of stone-based knowledge that is thousands of years older than we often care to admit. A laser beam sweeps silently across the weathered stones of the Parthenon, not to erase their history, but to read it with a clarity never before possible. This is the digital decoder, a suite of modern technologies like 3D laser scanning and photogrammetry that are finally allowing us to see the ancient builder's language in its full, breathtaking complexity. These tools create hyper-accurate digital models of entire structures, capturing every chip and curve with sub-millimeter precision. They act as a kind of Rosetta Stone for stone geometry, translating subtle, hand-worked details into a format we can measure and analyze, revealing patterns that have been hiding in plain sight for centuries. Suddenly, we are not just looking at a building, we are reading the master mason's mind. For generations, scholars debated whether the subtle curves of classical columns were intentional or simply the wear of time. Digital scans of the Parthenon delivered a definitive answer. Its majestic columns are not straight. They possess a gentle swelling known as intosses, a deliberate curvature engineered to counter an optical illusion. A perfectly straight column would appear to sag in the middle to the human eye. The builder's geometric refinement, invisible to casual observation, makes the entire structure appear more robust and perfectly upright. This was not crude construction, it was high-precision visual psychology carved in marble. Beyond aesthetics, these digital models allow us to peer into the very skeleton of a building. Engineers can now run sophisticated simulations, applying virtual forces to see exactly how stress flows through the stone network. We can watch the load paths travel down the ribs of a Gothic vault and out along the arcs of its flying buttresses, visualizing the perfect balance of forces that the master masons understood intuitively. This technological revolution does not dismiss the old rules of thumb, it validates them. We are discovering that the mason's empirical knowledge, passed down through generations, was rooted in a profound and correct understanding of physics and geometry. The digital decoder is not replacing ancient wisdom. It is finally giving us the vocabulary to appreciate its full genius, proving that the silent language of stone is more eloquent than we ever imagined. Chartres Cathedral rises from the French plains as a living testament to the master mason's art. Its very stones hum with a mathematical harmony, a geometric canon so pure and complete that it feels less like a building and more like a single, unified thought carved in limestone and light. The entire structure, from its sprawling foundations to its soaring spire, was generated from one simple, powerful shape, the square. This initial square was not a static blueprint but a living seed, endlessly subdivided and multiplied using the sacred ratios of the golden section and the square root of 2. From that first decision, every other dimension of the cathedral unfurled with mathematical necessity. The width of the great nave, the span of the side aisles, the precise placement of every pier and the height of every window, all were locked into an unbreakable proportional chain. This is why the space feels so deeply coherent, a silent music where every part resonates in perfect harmony with the whole. The famous labyrinth set into the nave floor is often walked as a spiritual meditation, a symbolic pilgrimage to Jerusalem. Yet its circular path, precisely 410 feet long, may also be a geometric key. Some researchers propose it is a scaled-down model of the cathedral's own proportional scheme, a full-size diagram of the cosmic order embedded in the very path the faithful walk. This intricate stone maze is a perfect metaphor for the building itself, a complex journey that is, at its heart, governed by an elegant and knowable logic. This geometric language extends to the very gateways of the sacred. The west front's royal portal and the magnificent transept porches are not merely decorated entrances. Their entire layout, the soaring height of their arches and the delicate spacing of their columns, is determined by complex constructions based on the pentagon and the triangle. These shapes were chosen not just for their structural integrity, but for their profound symbolic weight, embedding layers of spiritual meaning into the portals through which every worshipper passed. Chartres stands as a symphony in stone, a composition where every note is a perfect ratio. Its enduring power demonstrates how a single, brilliant master plan could be faithfully executed over decades, even centuries, by generations of builders who all spoke the same silent, mathematical language. Those polygonal walls at Machu Picchu are not just a static puzzle, they are a living system designed to dance with the earth. The genius of Inca stonework lies in its deliberate imperfection. Unlike the rigid, uniform blocks of classical masonry, each granite stone was uniquely shaped into a complex polyhedron with numerous facets and angles. When assembled, these blocks press against one another across dozens of tiny contact points, creating a state of constant, distributed pressure. This is the three-dimensional jigsaw puzzle you see, a technique known as ashlar masonry. But the true magic happens out of sight, in the microscopic spaces between the stones. These gaps are not failures of craftsmanship, they are engineered flexibility. During an earthquake, the entire wall becomes a dynamic entity. The stones shift and rotate minutely against each other, their multifaceted surfaces grinding and absorbing the violent energy of the tremor. The seismic force is not concentrated at a few weak points, but dissipated across thousands of tiny friction points throughout the wall's entire fabric. Once the shaking stops, gravity and the interlocking geometry simply guide the stones back to their original positions. This is the principle of dynamic stability, a concept modern engineers strive to replicate with advanced materials, yet the Inca achieved it with little more than stone hammers and an intuitive grasp of geometric physics. This profound understanding extends to the very openings in the walls. Look at any doorway or window in Machu Picchu, and you will notice its distinctive trapezoidal shape, wider at the base and narrower at the top. This is not an aesthetic whim, it is a calculated reinforcement. The sloping sides prevent the formation of straight, weak stress lines from top to bottom. Instead, the weight from above is channeled diagonally down into the sturdy walls on either side, creating a far more resilient structure that is incredibly difficult to shake apart. The Inca builders were masters of their volatile environment. They did not try to fight the immense forces of nature with brute strength. They chose to collaborate with them, using geometry to transform a potential weakness into the source of their architecture's legendary endurance. What other ancient wisdom might we be overlooking in our pursuit of modern, rigid solutions? A forest of stone rises from the prayer hall of the great Mosque of Cordoba, its striped double arches receding into a seemingly infinite expanse. This is not a chaotic thicket but a meticulously planned geometric grove, a space where the universal language of mathematics achieves a distinct and breathtaking accent. The entire structure is a symphony composed from a single, repeated note, the square. This fundamental module was the generative seed, subdivided to establish the perfect grid of columns that support the ceiling. The famous red and white stones of the arches are far more than decorative stripes. They are a visual representation of the underlying calculation, a rhythmic pattern that makes the building's mathematical heartbeat visible to the eye. This creates a hypnotic effect, a space that feels simultaneously vast and intimately ordered, guiding the worshipper through a physical manifestation of cosmic harmony. The system's true genius, however, lies in its profound flexibility. Over centuries, the mosque expanded not by creating new designs, but by simply adding more of these identical modular bays to the existing structure. The initial geometric code was so powerful and complete that it could be extended endlessly without ever breaking its own rhythmic rules. This principle of infinite expansion from a simple core unit stands as a stunning testament to the foresight embedded in its original design. The spiritual and geometric heart of the mosque is the mihrab, the prayer niche that indicates the direction of Mecca. This is not a simple alcove, but a breathtaking chamber of its own, a miniature architectural universe. Its form is an octagon perfectly inscribed within a square, a shape of profound symbolic weight in Islamic art. The octagon serves as a geometric intermediary, a bridge form that beautifully negotiates the transition between the earthly square and the divine circle. representing the connection between the material world and the spiritual realm. Every surface of this chamber is adorned with intricate, interlacing geometric patterns, each one a further exploration of the infinite, generated from the same core principles of circle and square that govern the master mason's compass. Here, the abstract language of ratios and shapes becomes a direct conduit for devotion, a silent prayer built in stone and tile. The great Mosque of Cordoba, therefore, offers a vital lesson in the universality of this architectural tongue. While its spiritual vocabulary and aesthetic are distinctly its own, the underlying grammar of proportion, modularity, and symbolic geometry is the very same one that built the cathedrals of Europe and the temples of antiquity. It reveals that this was never a single culture's secret, but a shared human inheritance for giving enduring form to our deepest beliefs. Our modern world is built on silicon and steel, yet it struggles to match the silent eloquence of ancient stone. We possess laser scanners and computer models, tools that can measure a wall down to the micron, but they cannot teach a stonemason the specific weight of a hammer or the resonant sound a block makes when it locks perfectly into its neighbor. This is the profound difference between possessing data and understanding a craft. We can analyze the chemical composition of Roman concrete, a material that has endured 2,000 years in seawater, while our own modern versions crumble after decades. We know it used a specific volcanic ash and a unique mixing process, but the living technique, the rhythm and timing known only to the Roman artisans who cast it, has left no manual. That knowledge was a physical wisdom passed from hand to hand and eye to eye, lost when the chain of apprenticeship was finally broken. The intricate polygonal joints of Inca walls present a different kind of mystery. We can create digital simulations of how the stones shift during an earthquake and settle back into place. A modern stonemason, however, could spend a lifetime trying to replicate just a few square feet of that work, lacking the generations of ingrained skill that informed every strike of the stone hammer. This was not just engineering, it was a high form of tactile artistry, a conversation between the craftsman and the rock that we can no longer overhear. The most significant loss may not be a technical recipe, but an entire way of seeing the world. For the ancient builder, a perfectly set stone was not merely a functional achievement. It was a spiritual act, a physical prayer that aligned human effort with cosmic order. The master mason did not separate the geometry of his arch from the cosmology of his culture. The two were a single, unified thought. We can measure the Parthenon's subtle curvature with absolute precision, but we cannot recover the cultural consciousness that deemed such a refinement essential for capturing the soul of beauty itself. Our modern approach excels at the how, but the ancient mind held the key to the why. This gap reminds us that their language of stone was more than a set of calculations. It was a vibrant culture with its own jokes, its own rituals, and its own unspoken understandings. And with the passing of that culture, some of the most beautiful and profound accents of its speech may have fallen silent forever. For the master mason, his compass was both a scientific instrument and a sacred object. This single tool could measure the physical stress on a stone arch while simultaneously tracing the symbolic circle of eternity, a perfect illustration of a world where faith and physics were not opposing forces but two sides of the same coin. His work was a devotional act, and the mathematics he used was the very language he believed God had used to write the universe. The cathedral was his ultimate expression of this unity, a structure where every calculated line served a dual purpose. The precise angle of a flying buttress was a triumph of engineering that channeled immense weight safely to the ground, yet its soaring arc was also a visual prayer, lifting the eyes and the spirit toward the heavens. There was no distinction between the technical and the theological, the geometric and the spiritual. this integrated vision fueled an era of breathtaking innovation. The desire to create a dwelling worthy of the divine pushed builders to test the very limits of stone and gravity, leading to the invention of the rib vault and the stained glass window. They were not just solving engineering problems, they were reaching for the sublime, using geometry as their ladder. This ambition was rooted in a classical idea known as the music of the spheres, a concept from Pythagoras and Plato that envisioned the planets moving in celestial harmony, creating a cosmic music inaudible to human ears. The medieval builders sought to make this silent music visible. They designed their cathedrals to be vast stone instruments with proportions and ratios that mirrored these heavenly harmonies. When you stand in such a space and feel an instinctive sense of peace and balance, you are not just appreciating the architecture, you are sensing the residual echo of that cosmic chord, frozen in limestone and light. This worldview stands in stark contrast to our modern habit of placing science, art, and spirituality into separate, walled-off compartments. We see a mathematician, an engineer, and a theologian as having entirely different jobs. The master mason was all three at once, and his greatest legacy is the proof that the most profound human achievements often blossom at the intersection of different ways of knowing. By recovering this holistic understanding of geometry, we begin to see what our own world, for all its computational power, might be missing. We have gained incredible precision in our tools, but have we lost the dimension of meaning that guided the hands which used them? The stones of Machu Picchu do not simply resist earthquakes, they welcome the movement, a principle modern engineers are now embracing to design safer cities. This ancient strategy of dynamic stability, where a building is engineered to sway and settle rather than fight seismic force, is inspiring a new generation of earthquake-resilient structures. Instead of relying solely on immense strength, researchers are developing base isolators and flexible frames that allow a skyscraper to ride out a tremor like a tree bending in the wind, absorbing energy that would otherwise shatter rigid concrete. This shift from brute resistance to intelligent flexibility is a direct lesson from the polygonal walls of the Andes, proving that the oldest solutions can sometimes be the most futuristic. Similarly, the medieval mastery of passive solar design is being rediscovered as a cornerstone of sustainable architecture. Just as a cathedral's east-facing altar was aligned to catch the morning sun on a specific saint's day, modern builders are now using sophisticated software to position windows, overhangs, and thermal mass, allowing a building to be warmed by the winter sun and naturally cooled by summer shadows. This is not new technology, it is ancient celestial alignment refined with modern materials, a perfect marriage of timeless geometric wisdom and contemporary innovation. The medieval system of modular construction finds its powerful echo in today's push for prefabrication. The same logic that allowed a Cistercian monk to use identical templates to build monasteries across Europe now enables factories to produce precise wall panels and floor sections that are shipped to a site and assembled with breathtaking speed. This approach drastically cuts construction waste, reduces energy consumption, and makes quality housing more accessible, demonstrating that the drive for efficiency through geometric standardization is as relevant now as it was 800 years ago. Perhaps the most profound lesson lies in the ancient focus on human scale and proportion. So much of our modern built environment feels overwhelming or alienating, with towering glass cliffs and vast, impersonal plazas. The ancient builders, guided by ratios like the golden section that mirror our own bodily proportions, created spaces that feel instinctively welcoming and harmonious. We are biologically wired to respond to these mathematical relationships, which is why a room with balanced proportions can foster a genuine sense of calm and well-being, a quality often missing in cost-driven modern design. This geometric language also champions durability and the use of local materials, principles that are central to today's green building movement. The ancient builders did not ship granite across oceans. They used the stone from the nearest quarry, understanding its properties intimately. They built for the ages, creating structures meant to serve generations, not just to meet a short-term financial timeline. This long-term perspective is the ultimate sustainable practice, challenging our disposable culture and reminding us that true value is measured in centuries, not quarterly reports. The silent language of stone geometry, therefore, is far from a dead language. It is a living repository of practical wisdom, offering us a blueprint not for replicating the past, but for constructing a more resilient, beautiful, and human-centered future. Their legacy is a challenge written in stone. These master builders were far more than laborers. They were philosopher-mathematicians who saw the universe as a great geometric code and their buildings as the key to deciphering it. We have walked from the primal alignments of Karnak to the luminous heights of Chartres, and from the dancing walls of Machu Picchu to the modular harmony of Cordoba's Mosque. Across continents and centuries, the same silent language was spoken, a universal grammar of circle, square, and triangle, adapted to express unique cultural beliefs while solving the eternal human challenges of stability and meaning. The profound realization is that these wonders are not happy accidents of history. They are the deliberate, intelligent application of a deeply integrated knowledge system, one where physics and faith, calculation and cosmology were understood as inseparable parts of a greater whole. Our modern tools, from laser scanners to acoustic analyzers, are not making these structures obsolete. They are finally giving us the ability to listen to their quiet, enduring wisdom. So the next time you pass an old stone wall, a cobbled street, or a venerable archway in your own town, pause for a moment, look past the weathered surface. You might just glimpse a page from that grand, global manuscript, a single sentence in the ongoing story of how humanity has always used mathematics to build a more beautiful and resilient world. If this journey into the hidden language of our built heritage has sparked your curiosity, we would love to hear your own observations or questions in the comments below. Consider subscribing to continue this exploration as we keep decoding the profound and beautiful mysteries left to us by